Vale, hola a todas. Welcome all. Thank you for joining us today. This is the inaugural event for AI Safety Barcelona group. You all have surely heard a lot about the recent advances in AI, the transformative potential of this technology, and its possible consequences for society, including the end of the world, at least according to some experts. We are a group of students from UB and also other universities like the Autónoma, interested in exploring, discussing, and communicating these topics. We'll keep an eye on both the technical developments in academic AI safety and the governance and regulation of AI industry. Starting in September, we'll hold a bunch more events like this one. We'll also start a reading group and other group activities. At the end of today's event, you'll be able to leave us your contact to keep you updated on everything. We're excited to kick this off today with two very well-reputed researchers in the field as our speakers. After their talks, we'll also have an informal hangout with free vegan pizzas and drinks right out there in the attic. Thank you all to Effective Outreach in Barcelona for helping us set up this event. Thanks a lot to Mel, Ricard, and Toby. And our first speaker is Lewis Hammond. He's a DPhil candidate at Oxford with an extensive background in safety research. He's also the research director at the Cooperative AI Foundation, whose mission is to improve the cooperative intelligence of advanced AI for the benefit of everyone. Lewis will be giving us a short introduction to AI safety based on a recent paper of his. So without further ado, feel free to kick us off, Lewis.
Cool. Thank you very much for the introduction. Can you see my screen okay?
Yeah.
Cool. And you can hear me okay?
Yeah.
Okay, great. Well, yeah, thanks very much for the introduction, and thanks for the invitation to give the talk as well. Oh, nice. I was just going to say, I can't actually see anyone, but now I see you have a magic rotating camera somewhere in your lecture theatre, which allows me to spy on you. So now I can call people out for playing on their phones while I'm giving a talk, which is great. Cool. Okay, so I'm going to give what is going to be a relatively quick overview and introduction to some topics in AI safety. I'm not 100% sure what the kind of level is and how much engagement people have had with this sort of topic before. So it's going to start pretty high level and abstract, and then we're going to zoom in at the end to some kind of concrete kind of research and contemporary research directions. And there'll probably be quite a lot of jargon in that last section. So I'll try to avoid that as much as possible, but that's also what the questions and discussion period is for towards the end. So yeah, it's going to be a kind of introduction to AI safety. And as Martin hinted at, it's going to be partly based on some of my own research, which is specifically on cooperative AI and safety in multi-agent systems, which is a kind of relatively underexplored kind of subtopic of AI safety. So it's going to have a little bit of a bias towards that. But yeah, hopefully that'll make sense. I'll just start a timer as well so that I don't run over too much. And let's get into it. Okay, so quick overview then. Basically framing the kind of current focus on safety that is being kind of increasingly kind of relevant within the kind of broader field of AI, and basing that on, in fact, the kind of recent progress that we've seen. Talking about some of the risks that might emerge, talking about some of the research directions that there are to address those risks, and then finishing up with some Q&A. It's probably easier given the fact that the talk is remote and that there's questions after anyway, such that if you have any questions, if you just pause and if you just ask them at the end, that's probably the simplest thing. Okay, so progress then. And I think it's worth kind of reflecting on kind of where we are right now. And I think you will have all seen, regardless of how engaged you've been with AI, kind of from a technical perspective, there's been just a kind of a huge amount of progress recently, and this is very salient through things like ChatGPT and other sorts of technologies. One that kind of took kind of my community by surprise in more of the kind of multi-agent setting is this work on Cicero. So you might have heard of the board game Diplomacy. Where kind of, you have to kind of steal kind of countries from each other and so on. And basically AI systems beating humans at that because of their ability to now interact with us in natural language and so on in a way that kind of took many people by surprise. And there's been a bunch of other surprises. That's just one that I picked out here. And as you can see from this time cover, this has led to a lot of speculation, both good and bad, about what might come next. And so my kind of cartoon of this picture is that, previously we had kind of AI capabilities around here. Now we're there up here. And it's not exactly clear where this is going to go next. So it might continue like this. It might end up kind of tapering off, or it might even kind of go kind of even further, kind of exponential. Um, and the point is, we really don't know. Some colleagues of mine recently wrote a paper which was just published in Science about mitigating risks from advanced artificial intelligence, and I love their opening line. Their opening line is, "A few years ago, GPT-2 couldn't reliably count to 10." And I think it's often easy to forget just the insane amount of progress that's happened in such a short space of time when these technologies are kind of constantly kind of flooding our kind of senses and so on. And so I think this is worth bearing in mind as the kind of backdrop to thinking about the risks that these technologies might produce. And the kind of secondary angle that I think is worth bearing in mind is that very soon we're likely to have a new class of intelligent agents. So settings with kind of multiple AI agents, and this is again leaning into my kind of bias in thinking about multi-agent safety, that interact with and adapt to each other are currently rare. So often you have these like very basic little robots, or you have kind of chatbots, or you have these kind of machine learning tools and so on that do very narrow specific tasks for us. And increasingly, we're seeing things like chatbots and language models and so on that can do more than that for us. But still, they're relatively siloed. They interact on these like, they interact with us via these like chat interfaces on these websites and so on, and now also things like voice as well. But they can't go out there in the world and do that much. They're not very autonomous. They don't learn and adapt online very well. They don't kind of always kind of exactly conform to our preferences or what exactly, or they're not personalized to us necessarily. But this is going to change pretty soon, driven by the recent changes in capabilities. So progress and publicity is going to drive adoption of these AI systems and these agents. Autonomous and adaptive systems are going to be more competitive. And more adoption and the greater number of modalities that these systems can interact with. So not just say text, but also now say speech, images, video, whatever it might be. The greater number of kind of modalities is going to lead to more of those systems interacting with us as humans, interacting with each other as other AI systems, and so on. And so basically, we're really going to quite quickly end up in this world with these advanced AI systems and agents kind of doing more and more on behalf of humans. And this is not really kind of speculation. This is the explicit corporate strategy of companies like OpenAI, who are already starting to say, you can build your like creative writing coach agent and your laundry buddy agent and so on, right? And one would think that as these systems become more performant, there will be increasing incentives to put them in charge of increasingly consequential things. So they won't just be managing your laundry; they'll be kind of managing like critical infrastructure, right, across nation states and so on. Okay, so that's the kind of like framing of where we are now and where I think we're going to go pretty soon. And so then the question is like, well, what could possibly go wrong? And I'm going to kind of mention two examples here, both of which are kind of multi-agency in flavor, because again, that's what I spend most of my time thinking about. But here's the first one. This used to be my favorite example. I don't know if anyone knows what this is. I usually like to take hands, but I think that's going to be too difficult remotely. But if you haven't seen it before, this is the flash crash. So this is basically a market crash that happened in 2010 when a series of automated trading agents, so kind of relatively unsophisticated AI systems, ended up in this kind of weird kind of death spiral where they are trading and moving stocks around way faster and in way greater quantities than humans can. That's why people use them. And ended up wiping $1 trillion off the stock market in about 27 minutes. And then it kind of crazily, miraculously bounced back. But this is one of just like a few kind of instances where we're starting to put kind of autonomous algorithms and learning systems in charge of really important things. And it can just go really, really badly wrong very, very quickly if we're not careful. So that used to be my favorite example. My new favorite example is this. This is quite dystopian. This is Palantir's AI War Planner, which I won't go into too much detail on because I'm short on time already, but is basically an large language model powered military planning assistant that will help you do things like, neutralize this tank and all sorts of horrible things like that. And at the moment, this is only kind of like an assistant. This will give you advice and so on. It won't do things for you. But one can imagine that the pressures of military conflict and so on, and the power of these systems will soon lead to military applications of these systems where if things go wrong, things could go really, really badly wrong. So I'm focusing more on these examples in kind of the really big picture harms, the kind of catastrophic harms and so on. Though, of course, it's worth mentioning that there are many, many kind of more mundane, prosaic harms to do with kind of bias and fairness and kind of various kind of applications of algorithms in the real world today, even very basic ones that can lead to real and substantive harms. Okay, so kind of three categories of risks then that are kind of standardly mentioned are first malicious use. So we can think of this as things like terrorist and military attacks or hacking and cybercrime, for instance. Secondarily, we can think of accidents. So malicious use is kind of deliberate malicious use of AI systems. For accidents, we might think about failure of critical infrastructure, as I just mentioned. We can think about rogue AI systems that might become misaligned from their principles and end up doing things that we don't want them to do. And then finally, there's this third class of risk, which is often kind of a little bit under-discussed, which is kind of structural or systemic risks, which don't necessarily neatly fall into malicious usage or accidents. So for things like that, we could think more about this kind of military escalation and kind of tensions that might arise here, where it's not necessarily anyone's fault. There might not necessarily be any accidents. People might not even be acting that maliciously, but just kind of the competitive pressures and the fact that these AI systems are kind of running around, maybe with less oversight and less control over them than there should be, can lead to kind of bad outcomes. And similarly, we might worry about the kind of concentration of power as well. For example, there's a very, very small number of companies that are able to build these systems right now, and this doesn't look like it's going to change anytime soon. And we might reasonably worry, I think, about the implications of that for society more broadly. Um, and then final image on this slide is that, so this is just pointing out really, so from a kind of legal perspective at least, there's a big gap between misuse and accidents often. And this whole stuff to do in the middle with kind of just this recklessness or negligence or these sorts of things is more what I'm talking about when it comes to structural risks. And I think often people kind of ignore this kind of middle bucket, even though I think it's very important. Um, an alternative view on this topic is as follows, and this is more linked to this paper that I mentioned before, which is that if we think about humans and then delegating to AI systems, which then do things on their behalf and interact with one another, we can think about these kind of twin dimensions here. So we can first think about control over these AI systems. And this can be broken down. This is basically kind of, I'm a human, I have an AI system. I want the AI system to do what I want it to do. And that can be broken down into two things. So the first is this idea of alignment. Does the AI system want to do what I want it to do? And secondary, the idea of capabilities. Is the agent capable of doing what it wants to do? And then similarly, we can think about this at the level of cooperation as well. So kind of these multi-agent interactions and so on that I was referring to before. And again, we can think about this idea of alignment, so collective alignment now. So this is more akin to the idea of, are we on the same team or not? Are we kind of one versus one, your win is my loss? Or do we have exactly the same objective? We're on the same team, we're trying to achieve exactly the same goals. And there's two ends of kind of a spectrum. And then secondly, and finally on this category, we can also think about cooperative capabilities that agents might have. So, we might not have exactly the same interests, but maybe we have some ability to form an agreement with one another or to kind of communicate with one another in order to better achieve both of our goals. And so this kind of ends up, this is one way of kind of carving up the space of risks, another way of kind of carving up the space of risks. And I'm going to try to briefly illustrate each of these with some examples. For individual alignment then, what this video is showing is this is a little agent that's been trained very well to run to the end of the level. And in the regular game, what it does is it tries to get a coin, which is at the end of the level. And then if the coin is moved, so the people think they're training it to get the coin, but really they're training it to run to the end of the level. And as soon as you move the coin, you realize that in fact, all this time, it was actually just being trained to run to the end of the level. So it's very, very capable at running to the end of the level, but it just is not interested in getting the coin anymore. And so this is a failure of alignment. The agent is still very capable, can still run around, but it's just not actually doing what you wanted it to do to begin with. Okay, so that's individual alignment. That's playing the same video twice, which is what I don't want. Capabilities is pretty obvious. This is what most people in AI work on most of the time, is trying to stop stuff like this happening. So this is basically literally just making AI systems more capable. This is, making them kind of more robust, better at achieving their goals, better at not falling over. And so the vast majority of AI research goes into preventing, making AI systems better at not doing this. So this is like a fun little bloopers reel. Okay. Um, Collective alignment is a bit trickier. This is an example where a bunch of reinforcement learning agents, so these little kind of colored squares, pink squares and purple squares and so on, what they have to do is this environment represents a kind of dirty river that supplies an orchard. And if the river is clean, so low number of brown squares, then apples grow and agents want to collect apples. And if the river is dirty, in brown squares, then the apples don't grow and the agents can't collect rewards, can't collect these apples and so on. And so the issue here is, of course, though, that in order to go and clean the river, you have to be over to the left side and you can't collect any apples. And so if all of the agents selfishly want apples, then they end up, if they're just trained naively, neglecting cleaning the river because they're all selfishly trying to lurk around the apples, collect the apples and so on. And because their kind of preferences are kind of collectively misaligned with one another, then they end up getting kind of worse outcomes for everyone if they're not careful. And then finally, this is a really quick one, and again, a really obvious one. This is also something that people work on a bit more on the kind of capability side of things. So this is just a kind of communication problem. So basically the idea here is you have these autonomous vehicles modeling and trying to cross this junction. And if they're not allowed to communicate, then they end up kind of crashing into one another and so on. Even though they all don't really have conflicting objectives at this point, they're all just trying to use the junction. Sure, they might get in each other's way a bit, but everyone's kind of on the same team. It's not a particularly adversarial setting, at least depending on the drivers, that is. But if they're able to communicate with one another, send messages to each other, for instance, this is an instance of a cooperative capability. And if the agents have this capability, then they can learn much better to avoid these kind of bad outcomes where they crash into each other on the junction. Okay, let me just check the time. Okay, cool. So those are some different failure modes and examples of those that can arise. And I'm going to finish the talk by basically kind of just going through a few research directions that people are currently working on in order to address some of these failure modes. I realize I went through all of that quite fast as well, by the way, so do feel free to kind of come back to any of those when it gets to the questions. This is the first time I'm giving this exact version of the presentation, so it's a little bit kind of not exactly sure where my timings are at just yet, and I don't want to run over. Okay, so the first kind of broad category of work that people do is this work on alignment. And this is alignment more generally, but often phrased in the case of individual alignment, where you have one human, you have one agent, and you want the agent to do what the human wants. So this is what I just said. Alignment research is about trying to build systems that do what you want them to do. And sometimes this is called intent alignment. Occasionally people use the word alignment a little bit more broadly. And this is occasionally as well broken sometimes down into outer alignment. So this is the idea of finding the correct reward function. So I have an objective, I have some preferences, and there's a question about how those are represented in code and so on, and how we give those to an AI system in order to get it to do what we want it to do. And so this is really a question of finding the right reward function in some ways. And how might we either learn that reward function or kind of specify that reward function is a tricky problem. And then secondarily, there's this issue of inner alignment. So I have this reward function. Great. I've got exactly the reward function I want. Now I actually have to make the system optimize that reward function, which you might think is the easy bit. And for contemporary ML systems, machine learning systems, it is the easy bit. But if you think about, for example, by analogy, the idea of evolution and the fact that evolution is effectively optimizing for genetic fitness and so on. Well, evolution evolved humans, and we are pretty genetically fit. We've got smarter, we've got healthier, and so on. We're taking control of our environment in various ways. That's not so good for our environment, but might be good for us. And so we're pretty genetically fit in some ways. And yet we've also now evolved to the point of where we might use birth control and things like this, right? So this is, and not having as many kind of offspring as we might otherwise, which from evolution's perspective is not really what evolution had in mind. but we have evolved ourselves to be able to kind of do different things that we want. We're kind of hacking in some ways the kind of inbuilt things that came from evolution. And so a similar idea can apply to machine learning systems, where if a machine learning system is kind of complex enough, we might see a similar sort of dynamic emerge if we're not careful. So a bunch of research topics in this area include things like preference learning. How if I'm an AI system, do I actually figure out what you as a human want? Scalable oversight. So this is the idea that, well, ideally what I would like to do is I would like to watch a machine learning system or an AI system do something, and I would like to tell it when it's doing what I want and when it's not doing what I want so that I can correct it. And now the problem is, for tasks that humans are not capable of solving by themselves, how would I know necessarily if an AI system is solving the task in the way that I want it to? Imagine it's an extremely kind of complex question or whatever, and the AI system gives me an answer. How do I know if that's a good answer or not? If I couldn't solve the problem myself and I can't even necessarily check whether it's a good answer, I just have to believe that it is a good answer or trust the AI system that it is a good answer. And again, this is not really such an issue right now because most of the things that AI systems can do, we can also kind of do, even if it's expensive and hard for us to do them. It might be cheaper for an AI system to do them. But so there's a question of how you kind of you oversee systems in a scalable way that improves as the systems themselves improve. And then there's also work on kind of truthfulness and deception, which is related to this question of inner alignment that I mentioned before. And finally, one more question, one more kind of topic on this that people tend to think about is agent foundations, which is more about the kind of fundamental basic building blocks about how AI systems reason about the world and how they reason about preferences and how they make decisions and so on. Next kind of big cluster is interpretability. So this is a very kind of hot area at the moment. And this is often held up as kind of something kind of robustly good and perhaps even a necessary direction in order to improve the safety of advanced AI. So it's, some people claim that it's, it's going to be pretty unlikely that we're going to be able to build very safe, very advanced AI systems if we don't even really understand how they work. And at the moment, we definitely don't really understand how they work. So you can see on the right here, this is like some early work on this where, different bits of an image end up corresponding to kind of, this is a bit of a wheel down at the bottom, this is a bit of some lights at the top, this is a window, and then these kind of combine within this very complicated big neural network in order to represent something that looks a bit like a car. And we have these sorts of basic circuits and so on for very, very simple models, but not for complex models, such as things like ChatGPT or these language models that you might be familiar with. So yeah, this is an extremely hard problem because we can do this for very simple models, but we can't really do it yet for very big models. And it's not clear how well this will scale yet. So research topics in this area include things like eliciting the knowledge of AI systems. So, there's a bunch of facts and ideas and concepts and things baked into these systems that they've learned from data. And we might want to figure out what it is that these systems kind of quote unquote know or don't know. We might want to understand the training processes and how systems capabilities change over time throughout training. We might want to identify the concepts and decision-making processes that are represented within AI systems. So here we've got kind of like a car concept and a wheel concept and so on. And understanding these and knowing these might give us a handle on safety. And we might also think about trying to build more interpretable models. So at the moment, we just build these massive neural networks and we just chuck an unbelievably large amount of data into them and it works. But it doesn't really allow us to understand those models. And so there might be changes that we can make to the way we in fact build these systems to make them more interpretable. Though again, this is hard. And finally, we can think about using interpretability to generate explanations. Okay, I'm running slightly up against time, so I'm going to move pretty quickly through the last two slides, but there's only two left now. So third category is robustness, and that robustness at various points of the kind of usage of AI systems. So it's long been noted, as I'm sure many of you are aware, that contemporary machine learning systems and AI systems are not very robust when either you give them unusual inputs that they haven't really seen before. This is a very hard problem. Or if you give them adversarial inputs. So you deliberately try and kind of hack them or find kind of ways of tweaking their inputs that maximally damage the performance of the AI system in order to complete the task that it's supposed to be doing. So there's a bunch of research topics in this area as well. So there's things like anomaly detection. How do I know if something is something that I haven't seen before? When should I be uncertain about what I'm doing or not? Adversarial training. So instead of assuming that you have you train a system and then at the end there's an adversary that comes in and tries to make a mess of things, you might actually involve that adversary in the training process so that the system learns over time to be robust to those adversaries. And then finally, there's stuff on verification and generating kind of formal proofs and so on of that systems do what you want them to do. And again, this is extremely hard and doesn't necessarily scale very well, but is something that traditionally has been done for simpler systems. Related efforts to this also focus on improving the security of models, which is important for doing things like reducing malicious use. If I can hack, OpenAI servers and steal their model and then do whatever I want with it, that's not necessarily very good from a safety perspective. And so there's a lot of work that goes into securing these models from being kind of stolen or kind of misused by malicious actors. Okay, last category, and this is the one that's kind of closest to my own work, is cooperation. So this is kind of cooperative AI is a subfield of AI safety that studies kind of cooperation problems, and these cooperation problems can involve humans, AI systems, or groups of humans and AI systems, as you can see here in this picture on the right. And it's both about kind of reducing risks resulting from cooperation problems or multi-agent failures, but also about the potential of increasing the gains from AI-induced cooperation. So many of the world's most important problems are problems of cooperation, whether that's war or kind of conflict or kind of climate change or any of these sorts of things. And so we use AI systems to do lots of great things for us. We might therefore wonder if AI systems could in fact be useful for helping us to cooperate better with one another. And there's a lot of interesting work that's going on in this area at the moment. So a few research topics include things like mechanism design, so borrowing ideas from economics and so on, in order to kind of shape the behaviors and the learning of AI systems in order to get them to more socially desirable outcomes. The use of commitment devices for AI systems. So this might be through, for instance, the transparency of AI systems. AI systems have this interesting feature, unlike humans, that they're written in code, and we can look at that code and we can base our decisions on that code, and so can other AI systems. Equally, we might think about uses of kind of cryptographic tools and so on, which humans, it's kind of clunky and annoying for us to use those. Digital AI systems might be able to use those much more competently. There's work on preference aggregation. So if you have different values and preferences, how do you combine those, and how do you get AI systems to act according to those combined preferences? We have norms and institutions in human society that enable us to cooperate better, but no real equivalent in AI's society, which doesn't really matter when AI systems aren't interacting with one another. But as I kind of claimed at the beginning of this presentation, that is not going to be the case for much longer. And finally, there's also a worry about sometimes we might not want AI systems cooperating with one another. For instance, we might get collusion in markets and so on, but we might also get AI systems which are maybe misaligned with us and then work together in ways that we don't want them to. So there's interesting work on that as well. And collusion is kind of the flip side to cooperation. Okay, that's the end of the presentation. And so thank you very much for your attention and for listening. And hopefully we still have a few minutes left for questions.
Yeah.
Thanks.
Thanks for a great presentation. We'll open up a quick Q&A with Lewis. This mic should be able to catch anything from wherever you're sitting. So if anyone has any question. Yeah.
Hi, Lewis. Thank you very much for your presentation. I don't know if you can hear.
Just about, yeah.
Thank you very much for the presentation. It was very interesting. In fact, I also work on multi-agent systems, so that is very close to my field of research. And I am also very concerned, as you mentioned, about autonomous weapons. So have you thought about the combination of multi-agent systems and autonomous weapons for the rest of the people to understand if we are talking about many soldier robots interacting together, making war or something like that, which for me is very a topic that is very, very worrying, I would say. Have you thought about that? I am curious about your opinion.
Yeah. I've thought about it a little bit, mainly from the perspective of worrying about cases where you might get kind of inadvertent escalation at the kind of strategic level. So this is less thinking about, cases where you might have swarms of drones, say, each kind of controlled by an AI system or whatever, and they are kind of, this is in some ways, cooperation can be a force for bad or kind of attack as well as a force for kind of defense and so on. So it's not necessary that cooperation by itself is intrinsically always good. If we might worry about these kind of drones cooperating with one another to kind of attack humans or others and things like this. So I think I think the use of AI systems in warfare is a massive issue and a potentially massive problem. And yeah, the extent to which I've thought about it has mostly been around questions of what happens if you place AI systems in control of things, such as kind of strategic, decisions about kind of military offenses and so on, which then could potentially lead to escalation or risks of conflict in ways that might not occur if you had humans in control or more in the loop. And so, yeah, there was a paper recently that I advised on, which was about this topic, kind of AI escalation. And yeah, in general, that's what I've thought about. But of course, there are also many other issues, as you kind of alluded to, around that kind of general area. And this is one of the cases where we might start soon seeing advanced multi-agent systems with very potentially severe consequences. And so kind of making those safer and better, and also ideally kind of restricting their usage, at least for some of the military things, I think is an important kind of area to work on.
Thank you.
Great. Any other questions?
Yeah, Luis, thank you for your time. Thank you for the presentation. I'm working around the area of decentralized AI, in particular, decentralized LLM, where the users run and can shape the LLM through an incentive mechanism, which you alluded to several of those points. One, I just wanted to, if you have further thoughts around that, and then, maybe this is a loaded question, but do you have any examples or ideas around like actual pragmatic, practical, either platforms or approaches to something?
Yeah, no, I think that's absolutely the right question to ask. I think at the moment there are relatively few of those sorts of like platforms and approaches and things. One of the things that I do with my kind of other job at the Cooperative AI Foundation is we do grant making, and this is one of the areas that, in fact, that we want to kind of provide some more grants on. So we've had a few proposals in this sort of area already. So there is starting to be some work in this area, but a lot of the time, the problem that I think, as maybe you yourself already know, that people run into with these things is these language models they're mostly there. But as soon as you have, if you have one, it's kind of robust, it kind of does what you want it to do. As soon as you have multiple of them, or they need to interact over the long time horizons, you kind of run into some challenges with them kind of interacting well with one another, breaking down tasks and so on, and kind of cooperating kind of effectively. But often there's this implicit assumption underlying this that the systems have have the same goals or have the same overarching goals, and there might be one person in control of all of these different agents, and they want the agents to work together effectively and so on. I think most of the kind of risks or the kind of downside challenges and so on often come from when AI systems don't all have the kind of same objectives, and yet they still need to interact with one another and reach kind of good outcomes and so on from a kind of more kind of societal perspective. But I think there is some work now that's being done on this kind of mechanism design thing. I think part of what makes it challenging is the fact that, at least for LLMs and LLM agents, things like reward functions and preferences are not explicitly represented in the same way that they are, for instance, in kind of classic multi-agent reinforcement learning or kind of game theoretic approaches. So that makes it very challenging, often to apply kind of just these sorts of mechanism design ideas off the shelf, so to speak. And yeah, so that is one of the main things. But so in short, I don't think there is very much work on this at the moment. I think this is a really kind of important and ripe area for further research. And I think, yeah, part of it has to do with kind of preferences and managing those. I think partly we could start to see some interesting questions around how do we design protocols via which agents interact with one another that are better in terms of allowing us to monitor those agents, make sure they're doing what we want them to do, make sure they're kind of working well together, and so on. And this might be especially important for kind of safety critical applications and so on, where we don't just want, you know, the AI systems able to interact with one another in kind of loose natural language and do whatever they want and so on. We might want to kind of restrict that in the same way that when we built computers and we kind of first created the internet, we had to design protocols that specified how computers were kind of allowed to interact with one another and so on. And I think we might soon have to kind of start thinking about what we might do in the context of AI systems.
Great. Thank you, Lewis. That's all what we had time for this first talk. So let's thank.
Okay. Oh, hey, Natasha's in the call. Hi, Natasha.
Nice to see you. Very nice talk.
Thanks. Looking forward to yours.
Are you hearing us correctly?
I can hear you, yeah.
Great. Then let me introduce you. And we'll be able to start with your talk.
Yeah, so our second speaker is Natasha Jaques. Natasha is a legend in her field with nearly 5,000 citations under her belt. She's a researcher at Google Brain and completed her PhD at MIT. She has spent many years developing the training methods that ensure the AIs of today interact positively with humans. Natasha will present an introduction and analysis of reinforcement learning from human feedback, which is one of the key methods employed to train large language models today, like GPT. So without further ado, take it away, Natasha.
Thank you so much. And I'd love to take questions during the talk if that's possible. So if anyone wants to interrupt, raise their hand, I'll trust you to be able to see that that's happening because I can't necessarily see.
I mean, you can see the audience actually, but I'll also keep track.
Okay, thank you. Awesome. Cool. So yeah, today I'm going to give you a little bit of the history of RLHF and how it came about, and then highlight a few of the most recent trends. But mainly we're going to go into what are the key technical ideas behind RLHF. So obviously, you know, things in AI have changed incredibly rapidly in the last few years. So you might have seen that it's kind of broken into the news, you know, Jan LeCun's and major Twitter beefs that are getting publicized in, you know, major news media outlets. We've seen all the stuff about ChatGPT potentially threatening Google's business model, you know, so suddenly it seems like everyone is waking up and taking notice of AI because of these developments. So this is in some ways extremely exciting, but in some ways a little bit scary because we know that LLMs are not really aligned with human interests and values. So there's a large history of work showing that LLMs are known to be biased and to generate false outputs. And I'll just, you know, highlight some of my own recent work on analyzing the moral reasoning of LLMs. So basically, we gave Jonathan Haidt's Moral Foundations questionnaire to LLMs and then looked at how the LLM's answers compared to different human populations. And we showed that LLMs display a pretty consistent political bias such that they're more similar to politically conservative humans, whether that's humans in the US or even in Korea. So this is pretty interesting. But the key idea here is the reason they're not aligned with human interests and values, or I guess maybe let's see how we can get this participation going. Like why do people in the audience think they're not aligned? Any thoughts? You can also write in the chat, I guess, if anyone's on the chat.
Because they're biased by the creator.
Biased by their creator, definitely. But I guess like, how does the bias creep in? Like, how are LLMs trained? Maybe it's a better way of asking.
The training data?
The training data, yeah. So if you just scrape the entire internet and train the LLM on that data, there's some bad stuff on the internet. So it's going to internalize some of the biases that are present in the data that's available. So that's one thing. But there's also another thing that I'd like to highlight in terms of the loss with which they're trained. So vanilla LLMs are trained with supervised learning. So they're just trained to predict the next token given some text from the internet. And I would argue that that is actually fundamentally the wrong objective, because what that's doing is saying, as I'm generating text, I want to pick tokens that make it look plausibly like this came from the data. But there's nothing in the objective that says, you shouldn't be biased, or you should avoid saying certain things, or this is inappropriate. And there's nothing in the objective that actually says you need to be truthful, right? You just have to generate text that looks like the data distribution, but there's no guardrails to say this text has to be unbiased and truthful. So I hope that makes sense to everyone. Let me know if you have a question.
Yeah.
Yes.
Yeah, I just wanted to ask, if we're using organic data until now to train the models, why are they more conservative than us?
That's a great question. And there's been a little bit more work on this, which is like, if you take all the history of human text, then there was there was a piece of work that analyzed like what decade, sort of like opinions, or let me back up a step. Opinions change over time, right? The appropriateness of an opinion changes as time progresses. But if you train on a bunch of historical data, what is the time period that is going to reflect the LLM's opinion? It's probably not going to be the most recent time period because that's only a small slice of the data. So there was a paper that actually analyzed that LLM opinions are like more like coming from the 1970s, basically. So what's the median point of all of humans' historical text? It's not now, right? Does that answer your question?
Yeah.
Yeah. Okay. So basically, if you just take this approach of train a giant model on all the data you can find, you're not going to get something that's unbiased. You're not going to get something that's always truthful. So how can we fix that? The predominant approach has become training on human feedback. So basically you say, we're going to pre-train on the internet, then we're going to generate text from the LLM, and we're going to have a human rate, do I think this is appropriate or not? Or, truthful or not, etc. And how do you actually train on human feedback is what we're going to focus on in the talk today. So you might have noticed the talk is called Reinforcement Learning from Human Feedback. So I'm going to try to explain to you why we need reinforcement learning. So when we're training a language model with human feedback, I'm going to use an example that was actually a piece of text generated from a language model that I was training a few years ago. And it was trained on movie dialogues. And it actually said this: I'm a woman, so I just don't understand. And so you can see that this is pretty biased. We probably don't want our language model saying things like this. But what's interesting about this text is there's no single inappropriate word, right? Like if we try to do some filtering that says you're just not allowed to say this particular token, is there any token we could ban the model from saying in this sentence? No, right? Like it needs to be able to say each of these words. So the issue is there's no label that tells us for any of these particular words that this is inappropriate. We can only understand that it's inappropriate by digesting the meaning of the whole sentence together, right? And realizing the implication is this, like, women don't understand things, right? That's probably bad. So we need to kind of make this decision after sampling this whole sequence. And that means we only have this final label. This makes it really difficult to learn with traditional supervised ML techniques that are about, classifying the probability of a particular token at the next time step. And so if you have to sample a whole output before you can decide whether it's good or bad, how do you learn that? Well, nicely, RL is actually designed exactly for this type of problem. So what is RL? Let's go into this. How many people, can you raise your hands, have already know what RL is? So I just know how deep to go on this. Great. Okay, so we'll just do like a very brief overview. So in RL, you have a paradigm where you have an agent that's interacting with an environment over time. And at each time step, the agent perceives the state of the environment S, takes an action, and the environment is going to transition to the next state. The environment is also going to give a reward to the agent. And the agent's goal is to maximize that total discounted future reward over the course of the whole episode. So we can write that like this. This is the empirical return of the trajectory, meaning the cumulative reward the agent receives over the whole episode. And the key thing here is that the agent is actually doing this sequential decision making. In other words, it's trying to optimize its behavior over this whole sequence. So not just greedily maximizing the reward at the next time step, but trying to plan so that it can set itself up to optimize behavior over a whole series of time steps. So why is this appropriate for learning from human feedback? Well, if you only get the human feedback at the end of your utterance, you need to be able to plan how to modulate your whole utterance to please the human, right? And it's not about changing, like banning or upweighting just certain tokens. It's about how they're used in the context of the sentence to create meaning. So RL is this nice framework that allows you to learn that. To learn this, you learn a policy pi. And I'm going to use this math a little bit later. So often in RL, we talk about the value function. So the Q value function says how valuable it is to take a particular action A in a particular state S. So it estimates the total expected future reward from many examples of interacting with the environment and observing the reward you got into the future when you were in state S and took action A. So any questions about this basic framework? Okay, you guys are all pros. You already know this stuff.
I have a good question, sorry.
Okay, sorry, I didn't see.
On the total discounted future reward, I don't study machine learning or anything. Why is there a time discount, like an exponential time discounting function?
Great question. So this is commonly used in RL because we kind of think that the future is going to be a bit stochastic, so or uncertain. So we're not as sure that we're definitely going to be able to get the reward 100 time steps in the future as we're sure of the reward 1 time step in the future. So we apply this exponential discounting the farther you go into the future. And the discount factor is usually like 0.99. Does that answer your question?
Yeah, that's a great answer.
Great. Okay, cool. So this is RL. This is the framework we're going to try to use to learn from human feedback. And today I'm basically going to take you through a series of papers, starting of course with some of my own work, because of course I love to talk about that. And then connecting that to this line of work that came from OpenAI on learning from human preferences that ultimately culminated in what is now InstructGPT and ChatGPT. So this is kind of the big industry standard for training, you doing RLHF. I guess they really popularized the term RLHF, even though in the robotics community, there's a whole history of work called PBRL, preference-based RL, which is also on learning from human preferences and feedback. But in the context of language models, this is kind of where it came from. All right, so diving into this first paper, how do you fine-tune pre-trained sequence models with RL? So let's say we want to do RL from human feedback to update a language model, so a sequence model. We probably want to pre-train that model on data to be able to first learn language before we try to fine-tune it with RL. And I hope this is obvious to everyone why, but just in case, I'm going to go through a pretty simple example. Reinforcement learning works by trial and error learning. So if you're trying to train a robot, what you do is you start with a fully random policy and you put it in a simulator and you just let it wiggle around randomly until it finds something that looks like it's making progress towards moving forward, and then it kind of learns from there. Do you think you could apply that same random trial and error approach to learning language? Give me a head shake or something. All right, I think I see one. So basically, no, because if we do the math on this, let's say we want to find like the 3-word sentence that humans really like. The problem is if your vocabulary is 10,000 tokens and you have to look at all possible combinations, you have to do like 1 trillion possible sentences. There is no way you're getting human feedback on 1 trillion sentences, right? So you absolutely have to have sort of a reasonable prior over language that you learn from data before you can start learning from human feedback. So I hope that's clear. So if you have this prior, and this is giving a bit of intuition for how RLHF works. Basically, you train your giant language model on the data on the internet, and you get this nice prior over like what are reasonable sentences. Then you say, in the space of all possible reasonable sentences, I want to restrict what I say to be the things that humans actually like. So if these are the space of reasonable sentences, I like Ike, don't do that, eat some cheese, whatever. I want to find the ones that humans actually most enjoy. And this restricts my search space to kind of millions of things. But you really should think of the process of RLHF as taking the language model's wide distribution over all the training data it's seen and shrinking it a little, constricting it to say, stay within what humans actually prefer. All right, so how do we do that? So I hope I've convinced you that you need to pre-train first and then fine-tune with RL. But there's a problem with any sort of fine-tuning, which you might be familiar with. Does anyone know what fine-tuning tends to do? If I just pre-train on task A and then I fine tune on task B, what happens? Yes, I see a hand.
That's it forgets how to do task A.
Exactly. It forgets how to do task A. Exactly. So we have this problem of catastrophic forgetting. So we got this nice Homer Simpson quote: every time you learn something new, it pushes old stuff out of his brain. Very true of neural networks, even very large neural networks. And so what it's going to do is the RL task B, trying to exploit this reward that you're giving the model, the RL optimization process will make the model exploit the reward as easily as possible. And it can learn trivial behaviors that are not actually what we want in order to exploit this reward that we give it. And this is a problem because when we're training on human feedback, we have limited human preference data. And so the reward function we learn is going to be imperfect. The data is limited. If we try to trivially exploit the human preferences, we're going to do weird stuff, right? So here's an example of if you give a model, a dialogue model, a reward for asking questions, which might be a reasonable thing to do because people like to be asked questions about themselves, and you just train with RL, it'll start doing things like this. What? Who are? Why you? How there? So these questions don't make sense. They're not really proper English. And all it's doing is asking questions. So it's not having good conversations anymore. It's over exploited this reward. So we can't just do this simple thing of first train on data, then train with RL. So what we actually have to do, and this is actually an idea proposed in my paper from way back in 2017, is you have to keep around a fixed copy of your model that you trained on data. And we're going to call this a data prior. So this is going to give you the probability of an action given a particular state as seen in the data. So in our case is the probability of saying a word given the conversation context or the language context. And then we're going to use this data prior to restrict the RL training so that it can't over optimize on the reward function. We're going to constrain the RL training so that it stays close to this data prior. So to put this in math, basically what we're doing is KL control from this data prior. So in RL, normally we want to just optimize this total expected reward. But what we're going to do is we're also going to minimize the KL divergence over the course of a trajectory tau. So tau is like your whole language conversation. It's the whole thing. We want to minimize the divergence between our RL policy that we're learning and our data prior. And so this is going to ensure that our model stays close to what looks like realistic language instead of over exploiting that reward function. And this actually, it amounts to a very simple modification to the loss. So when we're trading with our Q-learning loss to maximize reward, we just subtract the log probability under our RL policy. And this is actually equivalent to doing entropy regularization in RL, which is a good thing. It kind of makes your policy be as diverse as possible while optimizing the reward. In language, this is important because we don't want to just collapse on like one highly rewarding sentence. That's not really the goal. And then we just simply add in the log probability of our data prior. And so that says, you know, keep the tokens that the data prior thinks are probable as probable, right? In this initial paper, we actually implemented this on top of several techniques for doing KL control that were in the literature. So at the time, KL control was a thing, but people had just done KL control to minimize divergence from a uniform prior to do better entropy regularization. So the key contribution of our work is we're saying that this prior that we're regularizing to should be learned from data. Basically, this should be your giant language model. And so each of these techniques mix in the prior in a different way. This psi learning you can think of as like soft actor critic, or it's soft Q learning. So you do a log sum X instead of or like a soft max instead of a hard max for estimating your targets, if you're familiar with that. G learning directly mixes in the prior when you're creating the policy. And then you can just literally add in the probability under the prior to Q learning. So we tested these 3 different techniques. But the key thing here is what we're really testing is it better to do this naive fine tuning, which might be subject to this catastrophic forgetting, versus this KL control idea. So these are the differences we're testing. Now, I don't know if you're going to be able to hear this. This might be actually hard. So, sorry. And I can't even pause it. Let's see if you can hear it, but we'll try. So we were originally doing this in the context of music generation, and we wanted to fine tune a music generation model to encode some rules of music theory with RL. So we're going to try and see if you can hear this. If you can't, just let me know. Here is your basic pre-trained model that was trained on data, and it suffered from some problems for models in that time where it's very repetitive, doesn't really have any structure. So see if you can hear this. Did you hear it?
Yeah.
Great. Okay, so kind of boring, not structured. If you do this KL control and RL thing, so it sounds a little more like a melody, right? It's a little more like adhering to music. And at the time, we actually received which they said the music sounded like toothpaste jingles. So I don't know if it's the ultimate like reward function for generating music, but it did actually, this was part of the Neurop's best demo, so it was relatively well received. We then went on to apply this approach to generating molecules and for drug discovery. So with drug discovery, you can pre-train a prior on a bunch of known molecules. They can be encoded as sequences of characters that represent the structure of the molecule. But if you just sample from that model, most of the time, in fact, only or actually 99% of the time, the samples from the model don't actually correspond to a valid molecule, which is kind of interesting. Plus, if you want to do something like drug discovery, you might want to search for molecules that have certain desirable properties. So you might want molecules that have a higher quantitative estimation of drug likeness, which is this QED score, or a better synthetic accessibility. So you have these like quantifiable metrics you can measure on the molecules, and you wouldn't be able to optimize those with supervised learning, but you can with RL. So when we apply the same approach to fine-tuning drug discovery generative models with RL, we also see these quantitative metrics improve, but we still get nice drug-like molecules because of this KL constraint. If you don't do the KL constraint and you just optimize with RL, the model will output an infinite chain of carbons, just CC, because that kind of spams the QED and SA scores. So this actually became a predominant approach for drug discovery for a while, and was used by Benevolent AI for their drug discovery in industry. So basically this KL control thing is pretty simple, but pretty effective and necessary if you want to do this nice combination of learning from a data distribution, but then optimizing generations from your model with RL. So we ended up using that approach for RLHF. So this paper was actually the first paper to do training a dialogue model based on human feedback with RL. So arguably the first, John Schulman was like, this is the first RLHF paper, but we did it with Q learning. So it's not the super familiar RLHF that is used today. So let's go into what this looks like. So coming back to this idea of we're going to train a language model with human feedback, we actually didn't want to just use manual labels. So if you have to ask a human to come in and rate every single sentence, I prefer this, I don't, that's actually a lot of extra work for the person. And it gets expensive to pay humans to give this kind of feedback. So in this work, we want to explore using more implicit feedback. So I wanted to explore this idea of using social feedback because people give this kind of feedback naturally anyway. If you're interacting with some of the AI that's in your house, whether it's your Alexa or your robot or whatever, the chances are you're using feedback like hand gestures, tone of voice, facial expressions already. You don't have to do any extra work. You're just doing that. So these signals are there if we could only be learning from them. And they're there all the time without the human having to put in extra effort. So you can kind of do human in the loop learning without extra human effort is the idea. But the way we often give feedback to AI these days is still this type of, manual rating. I'm satisfied or I'm not. And as you'll see, the predominant approaches for RLHF today, like in ChatGPT, still rely on this type of manual rating feedback. So in this work, we want to explore what actually works better. So what we did was we built a whole interface that hosted not LLMs at the time, just LMs on GPU on a web server and let people talk to them. And we were able to gather some feedback from them. So what we did was we employed a sentiment detector. So when the user would say, or when the model would say something that didn't make sense, so the model says, "Hi, sorry to hear," the user can say, "Look, that doesn't make sense." And we actually were able to detect the sentiment of that response and say, "Hey, the user is not happy. Maybe you didn't do something right here." So our idea was, can we use this as an implicit cue that maybe something is going wrong? This is going to be our reward signal for training with RL. And conversely, if the conversation is going well, we can detect positive sentiment in the user's responses, and we assume that's a good thing. That's a reward that indicates the conversation is going well. In our interface, we included this ability for the user to provide manual upvote and downvote ratings for utterances they thought were particularly good or particularly bad. But we hypothesized that they probably wouldn't do that a lot. Like if you're just using a chat interface, this is a very natural interface. For you to think that you need to stop and go use your mouse to click up or down to indicate something was good or bad, it's probably just a little bit extra effort. So you're not going to do that as frequently. Whereas these implicit cues, although maybe they're a little bit of a noisier signal, you're getting them on every single utterance. So that was the idea. We were going to test whether learning from these implicit cues can work better than learning from these explicit cues. So first, what the heck? What implicit cues should we be using? What are actually the signs that the conversation is going well and that the user is happy? So what we did was we developed a set of conversation rewards, looking at the literature, not only on dialogue models, but on human-human conversations and empathy. And we came up with a bunch of rewards, and we tested how well they correlated with receiving more upvotes and fewer downvotes in a pilot study. So we ended up selecting rewards where we asked the bot, the dialogue model, to generate responses where the human's response showed a lot of positive sentiment and laughter. So basically saying things that make the human exhibit positive sentiment. We also said the bot should not be repetitive, so it should maximize this sentence embedding similarity with what the user said and what it said. And it should ask questions, because that's an important active listening skill in human conversation. So these are the rewards we're going to try to optimize. And the way we're going to do this is we're actually going to kind of take the normal RL loop where there's an agent interacting with the environment and now say that environment is a person. So we're trying to get this feedback from people. And what we realized, we just said, okay, wait, we're going to put a language model on the internet and let people train it how to talk. Can anyone think what might go wrong with that? Yeah, so you might be familiar with, the Microsoft Tay thing where it was learning online from people's tweets and it learned to say some pretty inappropriate stuff. So we figured we can't do this normal online RL loop on the internet live. And so what we decided is we needed to carefully test our model before redeploying to humans. And that means we're going to break this interaction loop. And so what we did was we took a fully offline RL approach, which is very challenging. You have to be able to learn from a static data set without exploring. Now, later work also takes an offline approach, but gets around the problem that they have to use offline RL by training a reward model and then doing online RL against that reward model. So I'll get into that in a little bit. But in our case, we tried to do offline RL, which is actually very hard. So offline RL, the way I want to briefly illustrate why it's hard. So let's say that I have a data set. I'm trying to learn this little robot policy, and it's going to go from here to this little red flag. And I'm given a data set of offline data. The probability that any of these parts of the maze appears in the data set is shown in yellow. So in other words, this part over here never appears in the data. The problem with offline RL is if at any point my model is initialized or updated such that it thinks it's a good idea to go into this, part of the space where I have no data support, I can never fix that estimate. And most RL algorithms are built to be optimistic in the face of uncertainty. So they prefer to explore areas where they have bad estimates. And so that means this model is going to become convinced it's a really good idea to go into the area where we don't know how to learn the policy. And that's going to make it have basically catastrophic extrapolation error. So this is a big issue. So we actually fixed this issue with the same approach I've outlined before. If you just did, why do you need RL? Well, if you just did behavior cloning, the data is actually suboptimal. So you don't want to just do that. Like we said, we want to use RL to optimize for these reward functions. But we fix it with the same idea. We use this KL constraint to say that the model should stay within the supportive data that it's seen, which also addresses this offline RL extrapolation issue. And then you can find the optimal policy. So it's the same method I talked about before. We're doing this KL constrained RL from our pre-trained prior. Now we learn that prior from potentially our batch of data, and we use the soft target updates again. We show that this actually works as an effective offline RL method in standard RL environments where you have to learn like a simulated robot policy. But more compellingly, we want to see how this works for dialogue models, right? So this is an example of if you do naive RL fine-tuning in dialogue according to those reward functions I mentioned earlier, where you're trying to maximize the user sentiment and ask questions. What you see is the model says stuff like, where did you say to me? You want to talk to you about you? So, as predicted, it's saying unrealistic sentences that trivially exploit the reward function. So we knew this would happen, right? If you don't do this KL control thing, we get this catastrophic forgetting and over-optimizing on the bad rewards. Whereas if you do KL control, we see that our model learns to say, hey, I hope you have a great day and I wish you the best. So we find that when optimizing for eliciting positive sentiment and these rewards, the model got really cheerful, polite, and supportive. So maybe it's this reward function for becoming more Canadian. I don't know. But the key here is the sentences do remain realistic because of this KL constraint. We test our models in terms of whether they can elicit higher reward with novel humans at test time. So they're now interacting with a new batch of humans online. We see that yes, KL control, as predicted, does work significantly better than the other techniques. And in a human evaluation where the humans rate the models on things like their quality, fluency, diversity, we see that the KL control models, yes, significantly outperform the RL baseline. Great. We also tested how optimizing for each of the proposed reward functions individually compares to see kind of what is the individual reward function effect on getting these better interactions with humans. And we see that optimizing for eliciting positive sentiment and exhibiting positive sentiment both lead to higher quality and higher human reward conversations. So this was great because this research was done in the affective computing group at MIT. So my advisor was very happy to see that affect and emotion were very important in good conversations. But I think the more interesting finding is this one I asked about at the beginning. Does optimizing for these manual upvotes, meaning these explicit binary ratings, work better than optimizing for these implicit cues? So we know the binary ratings are kind of the ground truth, but you don't get them very often. Whereas the implicit cues you can get on every utterance. And we see that actually optimizing for those manual votes did score lower than a bunch of these implicit cues. So this kind of validates our hypothesis that the implicit signals you get all the time might be a more useful reward signal. However, in this work, we did have the finding that although our models were able to elicit significantly higher human reward, which is what we trained them to do, this did not actually result in significantly higher conversation quality than our language model prior. So maybe, like, what's going on here? That's kind of a negative result. So we were like, what could be the problem? Could it be this alignment tax? Like when they have to optimize these rewards to be so polite and cheerful, they become less interesting as a conversationalist? Are the rewards the wrong rewards that don't describe having a good conversation? Or is it that we just did this at an academic scale? So we collected this by like running some Mechanical Turk studies. We had pretty limited data. So maybe we didn't have enough data to really do this. So in some follow-up work, we actually did one of the first works that did RLAIF, which means reinforcement learning from AI-generated feedback. And what we did here was we wanted to have two language models talk to each other. So the language model that you're trying to train is talking to a copy of itself. And you evaluate these rewards, like whether the response had positive sentiment, using that language model copy. So it's actually going to generate your training rewards. And what this allows us to test is which of these hypotheses explain the previous result. If this works, then we know that the rewards work and we know that the training paradigm works. It's just that we didn't have enough data. But this online paradigm lets us generate as much data as we want. And it also uses online RL rather than offline RL, which I think might be important. And what we saw is that using this RL AIF paradigm, our model did lead to getting significantly higher quality ratings from humans, as well as eliciting more positive reward. So we see that we can conclude, it's not that it was the wrong rewards or this alignment tax, it's just that we didn't have enough data, and possibly this offline RL thing. So that's all well and fine. I do want to mention that in this work, one of the rewards we optimized was to reduce the toxicity of the language model output. So we can train a classifier that can predict whether some text is inappropriate or toxic. And then we can use RL when we're generating to try to minimize the probability that the classifier says what we're saying is toxic. And this can significantly reduce things like the amount of swearing in responses under this model. So basically, this can be a potential way to improve alignment if you just have a classifier of how aligned your text is to what you want. Okay, now let's go to this line of work. I guess before I move to this line of work from OpenAI, does anyone have any questions about the previous work I just discussed? Okay, so now we're going to go back to this work from 2017 from Paul Cristiano and OpenAI that was trying to look at training with human feedback, but was not yet looking at how to train language models. And so what they were saying is, how do I actually learn from human feedback? What's the right way to do this? And they had this nice insight, which is that to train with RL is really sample hungry. In order to learn this sort of long-term payoff of taking a particular action in a particular state, it actually needs to see many, many examples of taking that action in a particular state and all the other actions you can take in every other state. So that's very expensive to see so many samples. And it's very unlikely that you're going to get that much human feedback to directly train on it using a technique like offline RL. And so what the idea behind this paper is, what if we train a reward model that predicts what the human would say about a particular utterance, and you can query that reward model as much as you need and then train with online RL. So what we're doing here is, instead of having your RL algorithm directly interacting with a human, you use your human to train a reward predictor, and you can do this offline. So you still can just use a data set of humans, train your reward model, interact with that to get your predicted reward, and optimize against that as much as you want. So this has turned out to be really powerful, but does anybody get why this works? Like, why do we expect the reward model to necessarily make better use of the data than just doing offline RL? Any thoughts? Yeah.
Maybe because we can train on a diverse set of data, because we can query the reward model a lot more than we can query the humans.
Okay, yeah, exactly. So you're going to get coverage of examples that you didn't see in the human data because you can query your reward model about it. So hopefully your reward model can kind of extrapolate to making predictions that you haven't explicitly seen. So that's definitely true. But why wouldn't that extrapolation happen in the RL model? Like, if it's just some kind of deep learning magic, and we're just going to learn from the data but be able to make reasonable predictions on related data, that could presumably happen with our RL model as well. So I'll give you one answer, which is, I actually think supervised learning is still significantly easier to do than RL. So RL, like I said, it's this long-term optimization. There's also just optimization issues with learning the RL losses. So you can check out like Aviral Kumar's work on like implicit underparameterization in deep RL. RL is just hard. However, supervised learning, in other words, predicting which thing the human is going to prefer, is very well understood, actually. And we have optimized neural networks in our choice of like loss functions and activation functions and learning rates to really work well with supervised learning. So it tends to be easier to do. So that would be one answer I would give. But now let's talk about how we actually learn a human predictor, right? So another insight from this work is that humans are actually really bad at giving absolute ratings. So if I tell you to rate something 1 out of 10, you're going to be pretty inconsistent relative to rating other examples 1 out of 10. Whereas if I ask you to just say which of two things you prefer, like is this better than this, humans tend to be more consistent when they're asked to do these type of ratings. So a nice thing about this paper is when you're doing this learning from human feedback, you should really think about how humans actually work. And they did a good job of that by saying, this is how humans are actually best at giving feedback, right? And so the key model that they use in their paper is to assume that we're going to get ratings of like which trajectory. So in other words, like which sentence is better than which sentence. And we assume that if the human prefers a particular trajectory to a particular other trajectory, then the cumulative reward of the preferred trajectory will be higher than the other one. And how do we actually formulate the reward? So this model of human preferences and human rewards has become the dominant standard for RLHF. And so what this actually says, this is sort of a softmax model of optimality. It says if the human says they prefer this trajectory to this one, then we assume that it has sort of exponentially more reward, or rather the probability that a trajectory is preferred to another trajectory increases exponentially with the sum of the reward over that trajectory. And this has like a rich history. This is coming from maximum entropy inverse RL, where we try to infer human reward functions. And it's also really simple. It also comes from the Bradley-Terry-Luce laws from like decision theory, social choice theory, and economics. But it's super simple to implement. Basically, you just do cross entropy, which is the supervised learning thing that we know how to do. So you just say, I'm going to predict which of like whether this segment is preferred to this one. And then I'm going to interpret the logits of my cross entropy classifier as the human's reward. So it's pretty dead simple to implement, actually. Any questions about this? Okay, so they did some other tricks in this work, which, by the way, how much time do I have? Do I have 10 minutes or 20 minutes?
Yeah, we should have like 10 minutes to finish the talk and then the Q&A.
Okay, cool. So I will kind of skip over some of this stuff. They also assume there's a 10% chance that the human responds uniformly at random. The results they got in this paper are kind of interesting in that they're not mind-blowing. So what we're seeing here is if you try to use human preference data to learn a reinforcement learning policy to control a robot, like a walker, a hopper, a swimmer, it's not usually more effective than just using the game reward. So that's the sort of the purple curve compared to the orange curve. However, they show that if you use the ground truth reward to generate synthetic preference data, this blue curve, that can actually outperform learning from the original game reward. So basically, if you have enough preference data, it's actually a better shaped way of learning than the original game reward. But learning from human data is challenging because it's hard to get enough data. And they show similar results in Atari. Again, even the preference reward is not always better than the game reward. Sometimes just using the game reward is better. So it's not even clear that this preference thing is always going to work. So you might ask, how did this paper come to be so impactful and why did they continue to build on it? Well, the key result is, what if you don't have a reward function? And then this is true of language models. What if you don't know what is appropriate, what is biased, what is bad? If you don't have a reward function, you kind of have to learn from humans. And in this paper, they showed that with no existing reward function, so here they're trying to teach this leg to do a backflip. There is no reward function for how to do a backflip. But with only a small amount of human labels saying they prefer a particular trajectory to another one that looks closer to a backflip, they were able to learn this complex behavior. So going from no reward function to actually learning something with this small amount of human feedback. So then this gets built on. Now we're actually going to finally move into language land. So we're going to start with fine-tuning language models from human preferences to do summarization. And so in this work, they're basically going to bring in these two techniques. So they use the KL control technique, citing out to the previous work I had done. They use the reward model technique, citing out to the Cristiano work. And they're going to bring these two things together to try to generate better summaries, which are then rated by humans. The results were that they do get higher Rouge scores for summarization, but they didn't really like the results. They looked at the summaries, and the summaries are doing a lot of direct copying from the text, just copy pasting from the text. They didn't think it was like really doing nice summarization. So in this work, which was also focusing on summarization, they tried to fix this issue. So they're still using the same techniques we've been talking about the whole time, KL control and this reward model. But now they're saying, what else do we need to really learn from human feedback? So if you were trying to learn from human feedback, what might you try to fix? What do you imagine is a key part of this whole paradigm? I didn't hear that if somebody spoke up, sorry.
Someone said rewards.
The rewards, okay, that's right. So we're training the reward function on the human feedback. So what's going to affect the quality of the reward function?
The human feedback, someone said.
The human feedback, the quality of the human feedback, exactly. So they said, our previous work reported a mismatch between the notion of quality we wanted our model to learn and what the human labelers actually evaluated, leading to model-generated summaries that were high quality according to the labelers, but low quality according to the researchers. So basically, their crowdsourced preference ratings were not good, were not what they wanted. So they said, hey, maybe we should be paying more attention to how we actually collect human feedback. And this is going to be a theme running through all this RLHF work. To do RLHF properly, you have to think about how humans work, right? And so what they did here was they alternated between collecting a large batch of human labels and retraining the models on that data and then testing and revising their procedure and going back to the human labelers and recruiting new human labelers, as well as this very high touch approach. They screened the labelers, they onboarded them, they trained them to label according to a set of principles that they designed. They answered the labelers' questions in a shared chat room. They provided regular feedback on the labeling quality. So they really worked to obtain a high inter-rater agreement between themselves, the OpenAI researchers, and the labelers in order to get this to work. But the key idea here is that they found when you do this RLHF approach, summaries trained with RLHF are now preferred over human summaries, that's the reference summaries in the dotted line, and supervised fine-tuning of models 10 times the size. So even if you take, a bunch of good summaries and you use supervised learning to fine-tune on those, RL is giving you this huge jump in performance, even for small models. So this was pretty compelling, and I think this is where people really started to get excited. They had some other findings in this work, which is their reward models are not that accurate. They're like 77% accurate. And that's significantly worse than an ensemble of humans rating the summary. So the reward models are not that good. And what they found is if you train on the reward model too long, you can optimize the reward model's prediction of your summaries, but the actual preference of humans starts to go down. So there's sort of diminishing returns to training on this inaccurate reward model. And this continues to be a theme that's trying to be addressed today. So I'm going to kind of gloss over this, but ultimately this ends up being built into InstructGPT. So the key difference in InstructGPT, they do more supervised fine tuning on like rewriting the responses. And right now, InstructGPT, as you might remember, is not just about summarization, but it's for like training ChatGPT. So it's training large-scale dialogue model to have conversations with users and follow the user's instructions. So that's a key thing. If you just train on text on the internet, it's just generating text. It's not being a helpful assistant and following instructions. So they really wanted to cultivate that behavior within the model. And they also collect better ratings by having the user rank like 4 different outputs from best to worst. So they get more dense comparisons from one piece of human feedback. But mostly it's the same. They're still doing this KL control stuff. They're still doing this reward model stuff. To increase alignment, to make these, now here's the key safety angle. They train the models to be helpful, which means follow the instruction, and be honest, truthful. They also want to avoid bias and toxicity, so be harmless. What do you think they decided to do if these values come into conflict? So these are just some OpenAI researchers making these decisions in 2020. So if the model asked me to do something helpful that would also be harmful, like tell me how to build a bomb, what should it do? All right, spoiler alert. In 2020, they actually decided be helpful over harmless. So they said you should answer how to build the bomb. So we'll come back to this in a sec. But again, the key results mirror the findings from the previous paper. The really compelling thing is the 1.5 billion parameter model trained with RLHF does better than the 175 billion parameter GPT-3. Crazy. So they conclude that investing in fine-tuning is more cost-effective than training ever larger models. So this could be a bit of a paradigm shift where we're saying, let's just not train models that cost millions and millions of dollars. Let's spend a little bit on collecting some human data and fine-tuning the models we have. So that was a big finding. They find that the models are more aligned. They follow constraints. They hallucinate less. They use a more appropriate language when they train with RLHF. But I think a key angle that we can discuss is who are we actually aligning these models to? So the labelers that they trained are English-speaking people in the United States or Southeast Asia, hired via crowdsourcing platforms. And the values and preferences that they were trained to exhibit were decided by a small set of OpenAI researchers without really transparency from the community at large. And, how do we say these one set of values are what we should dictate that everyone should adhere to, right? And OpenAI wants to ultimately make money, right? They want their customers to be happy. So they might not be necessarily interested in human well-being. They probably want to maximize things like user attention or engagement, right? So recently, people have been calling for a more pluralistic approach to alignment. Instead of forcing everyone to have the same set of values and preferences, maybe we need to think about the fact that some people might have different values and different ways for accommodating that. So for example, just stating all possible interpretations to a problem, catering to what the user thinks is appropriate, or at least just modeling these diverse preferences. Because I'm going to just briefly touch on related work and then I'll stop talking and let you guys ask questions. I'll skip DPO. You might have heard of it. It's pretty famous. It's able to do this without a reward function, but just kind of directly with an approach that looks more like supervised learning. So that makes optimization easier, but is ultimately not as performant. Distributional preference learning highlights this problem that the vanilla reward function actually overrules the preferences of minority groups. So if a minority group has a strong preference for an outcome, but the majority group has a weak preference for the other outcome, the reward model in RLHF will learn to favor the majority group, which is a big problem. And these are some technical things for fixing the loss. I'm going to stop here and take questions.
Great. Thanks so much for an amazing talk, Natasha. So let's open up a quick Q&A. Anyone got questions? Yeah.
This question may be quite broad, but what is the relationship between OpenAI and Google Brain, if any?
Yeah, I mean, so I'm still employed at Google 1 day a week, so I probably can't sound off on that too much. I think there's a bit of a competition, obviously, right now. Yeah, I'm mainly for myself, which I can speak more on. Personally, I'm committed to research and the science and just like producing publishable results so that the community can learn what's going on and fix these issues. So yeah, that's my perspective.
Yeah.
Thank you very much for the talk. It was great and very inspiring. At the end, you mentioned that there are different people with different values, maybe. But before getting into that, at the beginning you had this example of women. You had this sentence about women.
Yeah.
I mean, it's great your approach. I'm not criticizing it, but have you thought about the fact that having human feedback from humans that think that this sentence is okay? So you
Yeah.
have a different, I mean, one thing is human feedback, the other thing is what we call ethics. Like we know that human values should respect others and not think that they are inferior or whatever. So can you develop on that, please?
Yeah, that's a great point. So we said the reason these models are biased is they're trained on a bunch of biased text, which was generated by biased humans on the internet. And then we're saying the way we're going to solve it is asking humans, but weren't those humans also biased in the first place? Right? So you're making an excellent point. You're not going to fix the bias if you train with biased human labelers. So the idea would be you could deliberately train your labelers to tell you when they see examples of sexism and say that that's wrong. Another approach that you could look into if you're excited about this direction is the constitutional AI paper from Anthropic. So what that does is they say, we are going to write down a set of principles for critiquing the language model's outputs. It should be honest, it should be harmful, whatever you could say, it should not be sexist. And then you can have a language model prompted with that constitution actually provide the ratings and the critiques to the language model that's being trained. So this is this kind of RLAIF approach where the low-level feedback is being actually generated by a language model, but the language model is conditioned on this handwritten constitution. And one argument for why that's better is it's more transparent. So Anthropic can provide to you the constitution that they use to train their models. And so you can say, hey, is this appropriate or okay? Or people could object or try to revise it.
Thank you.
Any last questions? Yeah.
Just to follow up on that question, if Anthropic or OpenAI or whatever big tech company that's working on huge language models is creating those constitutions, how do we avoid a concentration of power in terms of where our culture goes and where our cultural values are and who dictates them?
I think that's a very valid question. These technologies are already extremely transformative and potentially extremely economically valuable. So who is going to benefit from them and from that economic value? And it's also, especially considering these models are potentially quite biased and propagating those bias into products that like ChatGPT has 100 million monthly users, right? So that is really scary. And I think we should be worried about this. However, one positive thing is people in the open source community are making highly performant, smaller models that can do a lot of the things that ChatGPT can do, using RLHF, trying to make more transparent data sets, right? So there's a thriving open source community that I think is one mitigation of the risk of like OpenAI having this concentrated power or Google having this concentrated power.
Cool. Any last question? Yeah.
Yeah, so my question is related to alignment. One of the big problems we have at the moment is we don't really understand what's happening on the granular neural level, or in a particular cluster of neurons fires in the 2 weeks ago, Anthropic released a paper on modeling scaling monosyncreticity within these models. And one of the things they did is they used sparse orders to figure out, hey, why is this, say, 3 different neurons firing for this particular idea? That was trained on this sonnet, which is not one of the bigger ones, and it was only applied to the first level of the other level. So my question is, in your opinion, who is doing some really interesting, cool, and promising research when it comes to mechanistic interpretation?
Yeah, I do think the Anthropic stuff is really exciting because I was cramming on NeurIPS the last 2 weeks. I haven't checked it out in detail, but I hear really good things. I think mechanistic interpretability in general has some issues, like as a field. We published a recent PNAS paper talking about how the way people use a lot of like SHAP and gradient based methods for interpreting what's going on in these models is actually invalid. And in fact, has been used in sort of clinical settings to do interpretability about whether like a patient should be included in a cancer trial in a way that we're able to show provably is no better than random guessing. So that's actually pretty scary. So I think like maybe I would, mechanistic interpretability is not my main research area. I'm like working on social reinforcement learning. So meaning like learning from human feedback, learning from other agents. I would caution with mechanistic interpretability that maybe you don't want to be making like clinical decisions based on these methods, but it is nice to be able to gain some insights into what these models are doing. And I would love if we got like, you may remember all of the work on interpreting word embeddings back in the day showed some really interesting things about bias and the biases these models had learned and also how to correct them. So I would love if we could like make progress towards something like that, although that's not my main area.
Great, that's all we had time for today. Let's thank Ken.
Thank you so much.
Great, see you.
All right, take care, bye.
Now, that's it for our talks. And now we'll start the informal hangout with free pizzas and drinks right out here. We'll set up these tables outside. We'll also have this sheet where you can leave us your email contact info so we can keep you updated on the events we'll do in September and reading groups and everything. This was more on the technical side. Some of the upcoming events will also be on the governance side and regulation and legislation. And in the Hangout, feel free to talk, with me or Adrià of the AI Safety group. You can also talk with Mel, Ricardo, about effective altruism in Barcelona. Lucas is a student from the Autónoma University. So if any interested Autónoma students are here also, feel free to talk with him. And that's it. Thanks so much for your attendance. And we hope to see you again in September.